tools that will define the next stage of human evolution. Innovation has propelled humanity forward since the dawn of civilization. From fire and the wheel to electricity and the internet, each leap in technology has altered the trajectory of human evolution. But today, we stand on the brink of a transformation that challenges the very core of what it means to be human. Brain-computer interfaces, nanotechnology, and genetic engineering, are these merely the next steps in technological growth, or do they represent something entirely new? Are these tools not just an extension of human capability, but a redefinition of what it means to exist as human? Let's dive into this future, filled with both incredible potential and weighty questions. At every stage in history, tools have extended our reach. Fire gave us warmth and cooking, farming secured food systems, the printing press unlocked knowledge for the masses, and computers introduced infinite possibilities. However, what makes the tools of today uniquely revolutionary is that they are beginning to integrate directly with our biology. These innovations won't just improve our lives, they may fundamentally change who and what we are. For the first time in human history, our future tools are not just about mastering the environment, they may be about mastering ourselves. Are these technologies a natural progression of evolution, or are they creating something else entirely? As we explore brain-computer interfaces, nanotechnology, and genetic engineering, we'll begin to unravel how these tools promise to alter both the outer and inner aspects of life as we know it. Imagine controlling your smartphone without lifting a finger, picture typing emails not with your hands, but simply through thought. Brain-computer interfaces, BCIs, are tools designed to bridge the gap between mind and machine, allowing us to tap into our neurons to manipulate devices and, potentially, the digital world. In simple terms, BCIs allow the brain and computers to communicate directly. Using sensors to read brain signals, these interfaces decode neural activity and translate it into external actions, such as moving a cursor on a screen or controlling a robotic arm. Futuristic, absolutely, but BCIs are already making strides, particularly in medicine. Take Neuralink, for example. The company envisions a world where BCIs can restore mobility to people with paralysis, enhance cognitive function, and even allow humans to download skills like playing the piano. The possibilities sound pulled straight from science fiction, but early prototypes have demonstrated significant promise. A paralyzed person controlling a robotic arm with their thoughts is no longer futuristic, it's reality. As BCIs advance, we're also looking at possibilities like transferring thoughts directly between individuals, perhaps creating a future where human communication transcends language altogether. While the potential is extraordinary, what about the risks? Giving technology direct access to our thoughts raises serious concerns about privacy, identity, and authenticity. What if your thoughts could be hacked? Could these advancements create a future where mind control becomes more than conspiracy theory? And how do we maintain individuality when connecting to shared neural networks? BCIs challenge not just the limitations of our bodies, but also the nature of who we are as individuals. Next, we shrink down to the nanoscale, smaller than the width of a human hair, where nanotechnology is poised to transform how we build, create, and heal. Unlike large physical tools of the past, nanotech operates at the molecular or atomic level, wielding extraordinary precision. Nanotechnology involves manipulating matter at an unimaginably small scale, measured in nanometers, to create new materials, devices, and systems. At this size, physics works differently, opening the door to innovations previously considered impossible. In the medical world, for example, nanotechnology offers the potential to work on the very building blocks of life, our cells and tissues. Consider cancer treatment. Traditional therapies often harm healthy cells alongside cancerous ones. Nanoparticles, however, can be engineered to deliver drugs precisely to affected cells, leaving healthy ones unharmed. This level of precision has enormous implications, not just for treating diseases, but for preventing them in the first place by repairing irregularities before they grow dangerous. But nanotech extends beyond medicine. Imagine a world with ultra-durable materials stronger than steel yet lighter than plastic, or water filtration systems capable of providing clean drinking water to millions using nanoscopic filters. These aren't concepts for the distant future, they're being developed as we speak. As exciting as this is, nanotechnology raises questions about safety and unintended consequences. Manipulating matter at the atomic scale could introduce new types of environmental or biological risks. How do we regulate something so small yet so powerful? And who gets to decide how this technology is used, with possible applications in weapons, surveillance, and other ethically murky fields? And now we turn to genetic engineering, the direct manipulation of life's blueprint, DNA. Imagine curing genetic diseases before a child is born. Envision altering traits like intelligence or physical strength. Genetic engineering offers incredible promise, but also some of the thorniest ethical debates in modern science. Using technologies like CRISPR, short for clustered regularly interspaced short palindromic repeats, scientists now have precise tools to cut and modify genes. This progress enables them to target and remove genetic defects, or even potentially improve upon them. CRISPR has already been used to treat rare diseases like sickle cell anemia and certain forms of blindness, but we're also beginning to explore altering more complex traits. Could we genetically augment intelligence or athletic ability? It's theoretically possible, and it raises enormous philosophical and moral questions. Genetic engineering forces us to confront significant societal challenges. Will this technology make life healthier, or will it elevate inequality? Wealthier individuals could potentially create designer babies with superior traits, further cementing societal divides. How do we make sure this incredible power isn't abused? Should limits be drawn on what aspects of life can be edited? This tool literally harnesses the power to play God, and humanity is far from united on how to use that power wisely. Alone, each of these technologies, BCIs, nanotechnology, and genetic engineering, is groundbreaking. But their power could multiply exponentially as they converge. For instance, nanotechnology could enhance brain-computer interfaces, allowing neural implants that heal the brain while providing advanced cognitive abilities. Similarly, genetic engineering could augment human intelligence, paving the way for better integration with BCIs and synthetic biology. This interconnectedness raises larger philosophical questions. If we can continuously upgrade the human body and brain, will the concept of being human still hold the same meaning? Are we stepping into a post-human future? While the potential of these tools is vast, significant challenges remain. Accessibility is one. Who gets to benefit from these advancements? If only the wealthy can afford enhanced intellect or nanotech-driven healthcare, will society fracture along new fault lines of inequality? Safety is another major concern. These tools are powerful, but their long-term impact on human health, the environment, and culture is still largely unknown. Genetic mutations, nano-accidents, or BCI malfunctions could introduce unintended, widespread consequences that humanity is ill-prepared to handle. Moreover, without widespread cooperation and strong regulations, the misuse of these tools could lead to catastrophic outcomes. These advancements cannot be left unchecked. Global collaboration and ethical dialogue are critical to ensuring these innovations truly benefit humanity. Let's pause for a moment to imagine two very different futures shaped by these tools. In the best-case scenario, these tools enhance human life in every possible way. BCIs unlock unmatched intellectual and creative potential. Nanotechnology cures diseases and repairs the planet. And genetic engineering eradicates suffering caused by inherited illnesses. Humanity might finally transcend its current limitations to achieve a new era of flourishing. On the other hand, in a worst-case scenario, these tools could bring chaos. A future where genetic inequality stratifies society, where nano-surveillance monitors every move, and where rogue BCIs compromise free will. These scenarios may seem like science fiction, but glimpses of these issues are already emerging. The choice lies with us. How will we navigate this convergence of possibilities and perils? As tech enthusiasts, futurists, and curious minds, it's our responsibility to engage with these questions early. Brain-computer interfaces, nanotechnology, and genetic engineering are no longer speculative. They're real, developing, and poised to redefine humanity. But with extraordinary power comes extraordinary responsibility. How will we decide who gets to use these tools and how they're regulated? Can we trust ourselves to wield such transformative technology wisely? And perhaps most importantly, are we ready to define and redefine what being human truly means? The future is coming faster than ever before, and the choices we make today will shape the world generations inherit tomorrow. What side of history will we stand on? One of empowerment and careful progression, or one of division and unintended consequences? Let's stay curious, stay thoughtful, and always ask, are these tools pushing humanity forward or somewhere entirely new? What do you think? Let us know in the comments.